Hey, what's up, guys? This is Dr. Vivek Palipuram, and I'm bringing you the next lecturette in ENGR 250 Probability and Statistics for Engineers and Computer Scientists. In this lecturette, we are going to discuss counting methods, and we are going to see how counting methods are used to count sample space, which are humongous, and find probabilities of different events associated with that sample space. Before we proceed any further, let's solve a problem pertaining to event independence. In my previous lecturette, I introduced you to the concept of event independence. Two events A and B are independent of each other if the occurrence of event B in no way affects the probability of event A. Essentially, we are saying probability of A given B is equal to probability of A. If you were to apply the conditional probability formula, you can write probability of A given B as probability of A intersection B or probability of B. And therefore, you'll find that this equation reduces to probability of A intersection B is equal to probability of A times probability of B. If this equation were to hold true for any two events A and B, then that means they are independent of each other. Event independence happens frequently in science and engineering. For example, let's say that you toss a coin twice. The second coin toss is independent of the first coin toss because the outcome of the first coin toss does in no way affect the probability of the second coin toss. But such event independence are not always apparent all the time. For example, consider this example here. You are monitoring a random 3-bit signal as a sequence B0, B1, B2. An example signal is 0, 1, 1. Essentially, we are enumerating all the sequences 0, 0, 0 all the way to 1, 1, 1. It's further given to you that the bits 0, 0, 0, or rather the sequence 0, 0, 0 and 1, 1, 1 have probability of 0.2 each, and that means others are equally likely with probability 0.1 each. We have two events, E1, two bits B1 and B2 are ones, and E2, number of ones is greater than or equal to 1. Are they independent or not? So it should be apparent from this problem that it is not clear whether E1 or E2 are independent. You cannot answer this question intuitively, unlike the coin tossing problem. So let's solve this problem mathematically. We have event E1 where two bits B0, B1 and B2 are equal to 1. And we are monitoring a bit sequence B0, B1, B2. So B0, B1, B2. So event E1 is such that B1 and B2 are equal to 1, 1. So that means these are the only possible outcomes in my event E1. E1 has these outcomes 0, 1, 1 and 1, 1, 1 with probabilities 0.1 and 0.2 each as given in the problem statement. I have another event E2, number of bits is greater than, or rather number of ones is greater than or equal to 1. So here E2 will comprise of these outcomes, everything else except for 0, 0, 0. So this will have 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, and 1, 1, 0 and 1, 1, 1. And the probabilities are 0.1, 0.1, 0.1, 0.1 as given in the problem statement, and the last one is 0.2. We need to find whether E1 and E2 are independent or not. Probability of event E1 will be equal to the sum of the probabilities of the outcomes in this event. So this gives me the probability of E1 as 0.3. And similarly, probability of E2 is equal to sum of probabilities of the outcomes in these events, which is equal to 0.8. It should come out to 0.8. Yes, it comes out to 0.8. Now, I need to find the event E1 intersection E2. Now here, I can see that E1 intersection E2, the items that are common to both E1 and E2 are 0, 1, 1 and 1, 1, 1. Essentially, it tells you that E1 is entirely contained in the event E2. So in fact, E1 intersection E2 is equal to E1. So probability of E1 intersection E2 is equal to probability of E1, which is equal to 0.3 again. Now, to find whether E1 and E2 are independent or not, I need to find out whether this equation holds true. Probability of E1 intersection E2 is equal to probability of E1 times probability of E2, whether this equation holds true or not. If I were to multiply the probabilities of E1 and E2, I find that I get the product as 0.3 times 0.8, which is equal to 0.4, which is not equal to 0.3, which happens to be the probability of E1 intersection E2. And therefore, E1 and E2 are not independent. This is how you will solve questions pertaining to event independence. If you are asked whether two events are independent or not, find the individual probabilities of the events, find the probability of their intersection, multiply the probabilities of the individual events. If this comes out to be equal to the probability of their intersection, then that means the two events are independent. Otherwise, they are not independent, meaning occurrence of one event does indeed change the probability of the other event. For example, if I were to ask you what's the probability of E2, or rather what's the probability of E1 given E2, so that will be equal to probability of E1 intersection E2, or probability of E2, which is equal to 0.3 or 0.8, which is equal to 3 over 8. So 3 over 8 is different than probability of event E1, 0.3. So occurrence of event E2 has indeed changed the probability of E1 from 0.3 to 3 over 8. All right, so that was an example of how to solve problems with respect to independent events. In this lecturette, we are primarily going to focus on counting principles. Specifically, we'll be developing different counting principles or counting methods that are used to count the sample space, which cannot be counted normally using pencil and paper. So far, we have analyzed experiments where sample space were quite countable. For example, in my previous example, the sample space comprised of sequences 000, 001, 010, and so on until 111, just 8 sequence. What if I were to ask you, hey, you know what, I'm analyzing a 64-bit sequence or a 128-bit sequence. How many outcomes are there in the sample space? Such experiments cannot be listed, or rather, sample space of such experiments cannot be listed on pencil and paper. Instead, we'll rely on the size of the sample space and the sizes of the events associated with this experiment to find the probabilities of those events. And for that, we need to rely on counting principles. Let's look into one basic counting principle, and which is what I call counting principle number 1. Let's say that an experiment is composed of 2 sub-experiments performed one after the other. If the first experiment has k outcomes and the next experiment has n outcomes, then this overall experiment is going to have n times k outcomes. So you just multiply the sizes of the sample space of these individual experiments, these individual sub-experiments, to find the number of outcomes in the entire experiment. For example, let's say that I toss a coin and then roll a die. So tossing a coin is sub-experiment number 1, and rolling a die is sub-experiment number 2. So if I were to find out what are the total number of outcomes in this entire experiment composed of these 2 sequential sub-experiments, then I'll find out their individual sizes of the sample spaces, so which is 2 and 6 respectively, and I'll multiply them and it gives me 12 outcomes, because I can get H1, H2, H3, H4 and so on until H6, or I can get T1, T2, T3 and so on until T6, giving me 12 outcomes overall. Similarly, consider an experiment. You roll a die, then you pick a card from a shuffled deck of 52 cards. How many outcomes are there? You can pause your video here and calculate the total number of outcomes in this experiment. Once you're ready to find the answer, you can unpause your video. All right, the total number of outcomes in this experiment will be 6 times 52, because there are 6 outcomes when you roll a die, when you roll a 6-sided fair die, and there are 52 outcomes if you were to pick a particular card from a shuffled deck of 52 cards. So that gives you 312 outcomes overall. So that is counting principle number 1, which is used to count the number of outcomes in an experiment that is composed of multiple sub-experiments. In fact, you have implicitly applied counting principle number 1 when you are performing your law of total probability problems using tree diagrams. Next comes counting principle number 2. Counting principle number 2 pertains to k permutations. A sampling without replacement technique. It's a sampling without replacement technique where you pick out k objects out of n distinct objects without replacement, such that order does matter. So what you're doing here, essentially, you have a box. Let's assume that you have a box that has n objects and you're picking out k objects out of it without replacement, without putting them back, and you're picking k objects such that order does matter. For example, consider that the box contains these 4 objects, A, B, C, and D. In how many ways can you pick 2 objects such that order matters? I can pick it as AB, then I can pick it as BA. Now, because order matters, AB and BA are distinct. Similarly, AC, CA, AG, DA, BC, CB, and so on. It gives me 12 outcomes. If you were to generalize this mathematically, and this can be proved using induction techniques, which I would not go into in this case, you'll find that the number of ways in which you can pick k objects without replacement such that order matters is n permute k, which is equal to n factorial over n minus k factorial, where n factorial is equal to 1 times 2 times 3 times so on until n. So apply this formula to find the number of ways in which you can pick k objects out of n without replacement such that order matters. This is counting principle number 2. Then comes counting principle 3. Let's say that I would like to pick k objects out of n objects without replacement, but I really don't worry about the order. In that case, the number of ways to choose k objects out of n distinguishable objects is going to be n factorial or n minus k factorial times k factorial, abbreviated as n choose k. So this notation right here is called n choose k. So if I were to ask you, hey, in how many ways can you choose certain number of items out of n? You'll say n choose k, where k is the number of items that I'm picking. Now notice here the similarity with the permutation formula. Now n choose k is actually n permute k or n pick k from my counting principle number 1, and I have k factorial in addition in the denominator. The reason why I have k factorial here, because the k objects that I'm picking, they can be permuted in k factorial ways, and each of those permutations mean the same thing. For example, A, B, and BA can be permuted in 2 ways, or rather A and B can be permuted in 2 ways, AB and BA. Now when I pick or when I choose items without replacement such that order doesn't matter, A, B, and BA leads to just one single entity. And similarly, AC and CA are just one entity, and so on. So essentially, if I were to divide this answer 12 by 2 factorial, because each of these guys can be permuted in 2 factorial ways, I'll get 6 as my answer. I can get 6 outcomes if I were to choose those 2 objects out of 4 objects without replacement such that order doesn't matter. Mostly in probability theory, whenever we deal with problems pertaining to, let's say, card problems or choosing balls from a bag, we will be using counting principle number 3 because usually we do not worry about the order. For example, if I were to have a shuffled deck of cards and I'm interested in picking out 4 red cards, the order shouldn't really matter here because all the red cards are technically same for me. There's rarely a game out there with respect to poker or with respect to card game in general where you worry about the order. You rarely worry about the order. And this translates well to science and engineering as well, where we are usually interested in outcomes where we do not worry too much about the order in which these outcomes are going to appear. Okay, there is one more principle that I wanted to discuss here, and I think I missed the slide for it. And that is, in how many ways can you pick k objects with replacement? Pick k objects with replacement. Meaning that I'm going to pick k objects out of n objects, inspect them, and I'm going to pick them up, place them back. How many ways are there? The number of ways will be n to the power of k. The reason is you have a container that has n objects. The first time that you pick, there are k possible outcomes. The next time you pick, let's say that you have a container that has n objects. The first time that you pick, there are n ways. The next time that you pick, there are again n ways, and if you were to do k times, there are k sub-experiments here, with each sub-experiment having n number of total ways. So by applying counting principle number 1, you will find that the number of ways in which I can pick k objects out of n with replacement is going to be n to the power of k. For probability problems, remember guys, we'll be relying on counting principle 3 more often than not. There may be cases where you may want to apply counting principle 2 or this particular counting principle right here, but such problems are rarely observed in science and engineering. Okay. With respect to counting principles, we'll be heavily utilizing this equation to find probabilities of events. Specifically, we'll be using counting principles to find the cardinality of the event, and we are going to find the cardinality of the sample space and divide the cardinality of the event by the cardinality of the sample space to obtain the probability of that event. These cardinalities will be obtained using counting principles. And let me show you some example. Consider that there's a deck of 52 cards which is well shuffled. A deck of 52 cards has 4 queens corresponding to ace, corresponding to spades, clover, diamond, and heart. Let's say that I pick out 7 cards at random. And what is the probability that you have no queens? What is the probability that you do have no queens? What you can do is pause this video right here and try to find out the size of the sample space. In how many ways can you choose 7 cards out of 52 cards without replacement? Order shouldn't matter here. So to find the probability of no queens, I'm going to find the cardinality of the event with no queens, or cardinality of the sample space in this case. Cardinality of the sample space is straightforward because I'm choosing 7 cards at random without replacement. You can assume that it is without replacement unless stated otherwise. I'm choosing 7 cards without replacement out of 52 cards. In how many ways I can do that? I can do it in 52 choose 7 ways. So that's the cardinality of the sample space, which happens to be the denominator term. Now concentrate on this event with no queens. So I'm looking at in how many ways I can pick 7 cards that are not queens at all. Essentially, what I can visualize is I can visually eliminate all the 4 queens. So I have 48 cards that do not have any queens. And if I were to pick 7 cards out of those 48 cards, then that would correspond to this event, 7 cards with no queens. So cardinality of event with 7 cards, no queens will be equal to 48 choose 7, meaning that I have eliminated the 4 queens out of 52 cards, so resulting in 48 cards without queens, and I'm just picking 7 cards from those 48 non-queen cards. So 48 choose 7 will be the size of the event, no queens and 7 cards. So I have found the numerator term and the denominator term. So the probability of no queens will be 48 choose 7 or 52 choose 7. That's an example of how to apply counting methods to find probabilities of different events. All right, now let's look into a little bit more complex example here. In a game of poker, what is the probability of a full house? A full house is 3 of a kind and 2 of a kind. What I would like for you guys to do is pause your video and try to work on this problem on your own. The size of the sample space should be straightforward because in a game of poker, we usually deal out 5 cards. So if out of a deck of 52 cards, if I were to deal out 5 cards, in how many ways can I do it? It is essentially answered by asking ourselves, in how many ways can I choose 5 cards out of 52? That answer is going to be 52 choose 5. The numerator term, the cardinality of the event of interest, is what is tricky here. I would like for you guys to focus on full house, 3 of a kind and 2 of a kind. Let me give you a hint. Full house can be considered as an experiment which is composed of multiple sub-experiments, which looks something like this. Full house consists of these sub-experiments. Choose a kind, where a kind is either ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, king, queen, jack. So there are 13 kinds. So choose a kind out of 13. Then after that, choose 3 cards from that kind. So you need to find out in how many ways you can choose 3 cards from that kind. Then you choose a kind from remaining kinds. And then you choose a card from that kind. If you were to find how many outcomes are there in these individual sub-experiments, and if you were to multiply them, that would give you the cardinality of full house. And ultimately, that is going to give you the probability of a full house. Please pause your video here, work on this problem on your own. Once you're ready, I'm going to show you the solution. All right, I hope you guys got the chance to look into this problem, and we are going to focus on a full house, which is 3 of a kind, and it is 2 of a kind. It's 2 of a kind. So the last one will be choose 2 cards from that kind. So let me focus on this problem one more time. To find the probability of a full house, I need to find cardinality of full house, divide that by the cardinality of the sample space. Usually for such problems, sample space is straightforward because in poker, I am considering a well shuffled deck of 52 cards and I'm dealing out 5 cards. So in how many ways can I choose 5 cards out of 52? That answer is going to be 52 choose 5. Because whenever we have a question in how many ways you can choose k items out of n, the answer is straightforward, n choose k, where k is the number of objects so that we are choosing. So here it's going to be 52 choose 5. So that's the cardinality of the sample space, which happens to be the denominator term. That's the most straightforward part. Now, the tricky part is finding the cardinality of a full house. So to find the cardinality of the full house, I can consider it as a major experiment, which is composed of these sub-experiments. Choose a kind out of 13 kinds. Now remember, each kind has 4 cards. So choose a kind out of 13 kinds. Then after that, choose 3 cards out of 4 from that kind. Once I've done that, I need to choose another kind now. And ultimately, I will have to pick 2 cards. So now I cannot use the kind that was used for choosing 3 cards, because if I have already drawn 3 cards out of 4, there's no way that I can draw 4 cards. So the number of kinds remaining are 12. So choose a kind from remaining 12 kinds, and then I'm going to choose 2 cards from that kind. If I were to find the size of these sub-experiments and multiply them, I'll get cardinality of the full house. So let's focus on this. Choose a kind out of 13 kinds. So I have 13 kinds, and the question is, in how many ways can you choose one kind out of 13? So that answer will be 13 choose 1. Now I have chosen that kind and I have 4 cards of that kind. Now the question is, in how many ways can you choose 3 cards out of 4? So that answer will be 4 choose 3. The next question is, choose a kind from the remaining 12 kinds. Now because I have already drawn 3 cards from the kind that I had chosen previously, I can no longer draw 2 cards from it because I have already drawn 3. There's no way to physically draw 2 cards from that kind. So that kind is eliminated, leaving me with 12 kinds. So choose a kind from the remaining 12 kinds. So in how many ways can you choose a kind from the remaining 12 kinds? That will be 12 choose 1. And then finally, choose 2 cards from that kind, which has 4 cards. So that answer will be 4 choose 2. Now these are the sizes of the individual sub-experiments. I'll multiply these sizes to get the cardinality of the full house. So probability of full house now is this entire multiplication term divided by 52, choose 5. So that gives you probability of a full house. Using the same principle, please solve this probability. Probability of 4 of a kind. If you would like to find the answer for this problem, 4 of a kind probability, please join my office hours on WebEx and discuss this problem with me. For your in-class participation problem on Thursday, you need to solve this problem right here. In a game of poker, find the probability of a flush. So please Google search what a flush looks like in the game of poker and find the probability for getting a flush. Again, for this problem, the size of the sample space will be 52, choose 5, because in poker we deal out 5 cards and there's 52, choose 5 ways in which you can deal out 5 cards. So the denominator term is set for you, and that is 52, choose 5. You need to find the cardinality of the flush event. That's for you to find out and submit it for the in-class participation on Thursday's class by 10 a.m. You can look at that, or you can upload that problem along with the other problems as a PDF on Canvas. Now let's go over another counting principle, and that is counting principle number 4. The number of ways or number of observation sequences for n binary states with 0 appearing n0 times and 1 appearing n1 times is n choose n1. This problem is quite pertinent to those people that perform analysis with digital systems. So consider that there are n bit positions. There are n bit positions, and each bit position can be either 0 or a 1. Now, to find out how many sequences are there with n0 appearing 0 times and 1 appearing n1 times can be answered as follows. It can be answered by asking a question to ourselves, and that is, in how many ways can I choose n1 spots to place ones out of n spots? And that answer is n choose n1. Similarly, if I were to ask you, hey, in how many ways can you observe sequences that have 0 appearing n0 times? That answer will be n choose n0. This is the number of ways in which 0 appears n0 times out of n. So that's counting principle number 4, which is used to enumerate the sequences for those cases where you perform multiple sub-experiments, where each sub-experiment has binary outcomes. Either it's going to be a success or a failure, 0 or a 1. That's counting principle number 4. Okay. As an example, consider this problem. Let's say that you take a digital design class at University of the Pacific with either Dr. Mueller or Dr. Basha or Dr. Ken Hughes, and there you're designing a module that detects whether or not the Earth will be shot by a death ray from the extraterrestrials. Now, the extraterrestrials are going to shoot a death ray if you receive exactly 13 ones in the sequence out of 32-bit. So now the question is, in how many ways can you receive a death ray? So the question is, in how many ways can you receive a sequence, or how many sequences are there such that there are exactly 13 ones? So this question can be answered by asking a question to ourselves, and that is, in how many ways can I choose 13 spots out of 32 to place my 13 ones where others are zeros? So that answer is 32 choose 13. So that's a straightforward question and straightforward application of counting principle number 4. There's one more counting principle that I would like to discuss here, and that is counting principle number 5, which looks similar to counting principle number 4. But before I give you counting principle number 5, I would like for you to solve this problem. I have 5 rings. I have 5 rings. 1 ring is from bachelor's, 1 ring is from master's degree, 2 rings from PhDs, and I have a 1 wedding ring. Let's say that the wedding ring is placed on my ring finger. In how many ways can I place the remaining 4 rings on my hand? So I have my hand that looks like this, like that looks like a dog's hand, or rather a bear's hand. Let me draw a human hand. Okay, apologies for my my drawing skills. Okay, so consider that this is my hand. Actually, it's not that fat. My wedding ring is placed right here. My wedding ring is placed right here. Now, let's say that I have one ring from bachelor's. I have two different rings from master's. And I have one ring from my bachelor's, one ring from my master's, and two different rings for PhD. So let's say two P1 and two P2. In how many ways can I place these four rings on the remaining four fingers? You can pause your video right here and tell me in how many ways you can do it. This can be considered as multiple sub experiments. You can choose a ring at random and you can place it in one of the four fingers, with an assumption that each finger will hold exactly one ring. And this can be performed as a sub-experiment. You choose a ring, you place it on one finger, then you choose another, you place it on another finger, and so forth. Okay, so I hope you guys got the chance to solve this problem. Now let me share this answer with you. Now I have four fingers remaining because one ring finger is already occupied by my wedding ring. Now, let's say that I want to place one bachelor's ring on one of the four fingers. So the question is, in how many ways can I choose a finger out of four to place my bachelor ring? So that answer will be 4 choose 1. So 4 choose 1 is the number of ways to place a bachelor ring. Now, next, let's say I would like to place my master's ring. Now there are only 3 fingers available. So now the question is, in how many ways can I choose one finger out of 3 to place my master's ring? And the answer is 3 choose 1. Then I have 2 PhD rings and I have 2 fingers. Now the question is, in how many ways can I choose 2 fingers for my 2 PhD rings? And the answer is 2 choose 2. And if I were to solve this, if I were to simplify this further, I get something like this: 4 factorial over 3 factorial times 1 factorial times 3 factorial over 2 factorial times 1 factorial times 2 factorial over 2 factorial times 0 factorial. In mathematics, 0 factorial is equal to 1. So if I were to simplify this, I will get 4 factorial times 2 factorial divided by, my apologies, 3 factorial cancel each other. I somehow read this as 21, but this is 2 factorial. 2 factorial and 2 factorial cancel out, and it gives me 4 factorial over 1 factorial times 1 factorial times 2 factorial. So this equation can be written in a nice choose format, and that is as follows. Let's say that you have n spots. The number of ways in which you can place the object 0, let's say n0 times, object 1 n1 times, and object 2 n2 times is n choose n0, n1, n2. So that is counting principle number 5, which deals with multinomial coefficients. So when you perform repeated sub-experiments n times, where each sub-experiment can lead to m outcomes, S0, S1, S2, and so on until S of m minus 1, then S of 0 appearing n0 times, S of 1 appearing n1 times, and so on, and S of m minus 1 appearing n of m minus 1 times is given by this factor right here. Let's solve a problem based on counting principle number 5. So let's say that you're testing 16 circuit elements, where each element can be either a high voltage H state or low voltage state or a high impedance state. In how many ways can you choose, or can you observe 6 high elements, 8 low elements, and 2 high impedance elements? And the answer will be, out of 16 elements, choose 6 for high voltage, 8 for low voltage, and 2 for high impedance state. That's your answer. Those are the total number of ways in which you can observe 6 high voltage, 8 low voltage, and 2 high impedance elements out of 16 elements. All right. I think it's a good time to stop this lecturette video right here. This lecturette video dealt with mostly counting principles, which will be used to find probabilities of events that have really large sample space. In my next lecturette, I'm going to discuss some problems associated with counting methods and independent trials. The next lecturette will introduce you to independent trials. Adios, guys.